Hello and welcome to Enhancing ETD Topic Modeling, a framework integrating LLMs for improved digital library discovery. Sharing this information with you is Upendra Dasu from Virginia Tech, Satvik Chekuri from Virginia Tech, William Ingram from Virginia Tech University Libraries, and Professor Edward Fox from Virginia Tech University. My name is John Hagen, and I'll be your moderator for the next 50 minutes. During the concurrent sessions, one session will be held in the main room and the other in the session room, breakout room where we are now. So if you are not in the right room, you can certainly navigate to the other, but please stay with us if you will. We will reserve 5 to 10 minutes toward the end of the session for discussion. A quick reminder before we begin, during the presentation portion, participants, please keep your audio muted. And please feel free to use the Zoom chat tab to ask questions, which will be addressed during the discussion segment. Thank you all for joining us, and now I'll turn it over to Prad and everyone. And thank you. Prad, go ahead, please.
Um, Good evening, everyone from the East Coast. Thanks a lot for the introduction. Let me share my screen. And if someone can just verify if you can see my screen.
It looks good.
Yeah. All right. Hello, everyone. My name is Pradyumna Dasu. Can address me Prad for short. I'll be today introducing our research, which is enhancing ETD topic modeling. We created a framework integrating LLMs for improved digital library discovery. Um, I, um, so to give you a brief overview of what I'll be covering today, I'll introduce our research, and following this, I'll talk about the data sets and also a bit of literature review to give context regarding topic modeling over the years and how we have enhanced the data that we use for this research for topic modeling using newer methods and develop a enhanced framework for topic modeling where we integrate large language models. I'll conclude with a few results and discussion points that we found interesting and conclude. And I'll take questions in the end, but feel free to ask me any questions in between. I'll present for about 35 minutes and then we can go with the questions that you have. So, to set context, we all know, as most of us work with scholarly content on a regular basis, ETDs research papers are growing at a rapid rate these days with lots of challenges, uh, consequently, to properly organize them, and accessibility being an issue with browsing, searching, and recommendation of these data. In Virginia Tech being pioneered the ETD research, also leads efforts for global accessibility of ETDs in particular. Now, what was the motivation that actually um, helped us with this research was that digital libraries need better browsing, searching, and discovery mechanisms, and ETDs, as we all know, which are growing at a rapid rate in with interdisciplinary research, have specialized vocabularies and newer terms coming in that complicate this existing browsing mechanisms and content discovery. And we feel topic modeling, which was originally a text mining technique coined many years back, can still aid exploration and discovery for these documents. However, topic modeling, which is the main concept of finding hidden themes amongst a large data set, essentially has its own challenges because we need to ensure semantic coherence and interpretability when it comes to topic modeling, and ETDs, as we have already established, being complex heterogeneous data sets, lack that, and topic modeling algorithms right now are more keyword based representations. The themes or topics that you uncover are still keyword based, which fail to capture thematic relationships sometimes. And that is where we came up with a solution where there's a possible solution to integrate the existing topic modeling algorithms and the large language models that we have access to right now. Now, what are the research questions that we're trying to answer as part of this work? Was to see if custom pre-processing techniques for text um, and enhancing this text impact the topic modeling algorithms as a first step, but also identify what are various advantages and limitations um, that come with these topic modeling algorithms for ETDs, but also identify how effectively LLMs can actually enhance topic representations in ETDs. Um, as our next section, I'll be talking about a literature review, briefly talk about the evolution of topic modeling over years. Um, we have classified topic modeling into four major eras, which is latent semantic index. I mean, the classical era where you had the latent semantic indexing probability, LSI and LDA, and the I'm sorry, um, the temporal analysis being integrated in probabilistic era, and the dynamic topic modeling coming in, or some of these improvements in the early 2000s. But however, with the neural era, we have the broad LDA and neural LDA um, algorithms that were more uh, integrate the original LDA, which is more popular, or the topic modeling as a word, which was coined along with LDA algorithm and integrated with neural networks, was where the neural era is what we're talking about in the year 2017. But since then, we know that the introduction of the transformer architectures in 2017 has changed the world essentially with the strength of contextual embeddings. And this is where our main focus is for our work, because the introduction of contextual topic models or BERT topic, which is another popular topic modeling algorithm, and the baseline in this era um, is what we are going to focus on, and how LLM integration has further improved over the recent years with topic modeling. Yeah, I should have um, done that. I'm sorry about that. Um, but yes, these points essentially cover what I have actually talked about until now. And I can take this question: to what extent does appropriate prompt engineering enter into search and using AI applications? Um, can I take these questions in the end, if that's okay with the moderators?
Yes, please. Thank
Yes,
you.
thank you. Yeah. Now, when I talk about topic modeling, they're mainly unsupervised learning mechanisms where we don't have ground truth data with related to these algorithms, and that's where evaluation of these topic models also becomes a complex process. But over the years, there are some popular methods that measure coherence within these topics, which means what do these words or topic representations, uh, semantic relatedness is within a topic, but also diversity within topics formed, meaning how good are the topics with how they're distinct and non-overlapping words. But then um, topics can also be subjective in many cases, is what we have understood from various literature. And human interpretability is where we assess these topic representations through manual evaluations using surveys or any interactive elements that we can integrate. Now that I've covered a brief section of what or how topic modeling has evolved, I want to introduce our data sets. And when I say data sets, we use ETD metadata for topic modeling and scalability testing of our mechanisms. Now, essentially, for purpose of this research, we have used three major data sets, which is we referred the large ETD data set as uh, a data set containing 520,000 documents metadata for ETDs from 42 US universities. And we just use this for scalability validation of our methods. Um, but the actual development that we did was using the curated ETD dataset, which has around 9,400 um, ETDs metadata, and this is a subset of the larger ETD dataset that we were talking about. This is where the detailed experimentation of our methods was done, and the introduction of 20 news groups dataset, which has around 18,000 um, 846 um, rows of text data is a public benchmark data set and is more popularly used while comparing algorithms and experimentation. Now, this is only used to compare what the text complexity is because we know that ETDs have, or scholarly content in general, have complex data or complex vocabulary in there, but comparing it with a general purpose text data set was something we wanted to do to identify um, the actual truth. Now, I wanted to add more on the curated ETD data set because it's something that is used for experimentation here, and it has a broad coverage of various disciplines, as and you can see the frequency from the department distribution is equal. Um, Now we have used ProQuest. The curated dataset has a column which categorizes each ETD into a ProQuest department category, which we have used to compare our results using embedding based scores, which I'll cover in the coming slides. Um, but most of the scholarly content is also from the 2010s, but we have papers from the 1930s to the 2020s. Now, the comparison that we did for the three data sets is comprised in this table or summarized. Um, Overall, the curated and large ETD dataset have higher vocabulary size, which makes sense with the amount of data in there. But also, if you identify the average sentence length is also much higher, which means the sentences are much longer. This is an important factor because we have used something called the Flesch-Kincaid readability score, which was introduced um, in the 1970s by the US government to identify what the readability of technical documents or army documents are, and which is still widely used as a metric to identify how complex texts are. And we have identified that the ETD data sets are more complex according to that metric, while also comparing sentence lengths and document lengths in average and the vocabulary size. Now, we have got an idea here that yes, the ETD data sets, at least the data sets that we are working with against the 20 news groups, are more complicated and tough to handle. Um, yes. Now we have the data set. Now, naturally, the next step in any natural language processing um, project or experiment is to actually prepare your textual data for topic modeling. Um, so that's where we have also prepared a custom pre-processing pipeline for ETD data. This is because of the complex academic writing and domain-specific terminology. And our goal is to prepare high-quality text inputs for the experimentation. Now, we have the regular text normalization, tokenization, stop word removal, um, lemmatization, and text enhancement methods that kind of pre-process our text to make it more maintainable and also gives a better handle on the algorithms and doesn't bias it with a few words that are not required. This is where we have introduced something called as LLM assisted stop word removal because during my experimentation, personally, when the vocabulary size is so high and we are working on a specific domain that is scholarly content, um, stop word removal is an important step where you want to remove all the noise from the text that you don't want to use. Um, Simple examples are words like is, for, and other words that are present in general stop word lists by popular um, libraries out there like Gensem and NLTK. But then, if you see the words like analysis, research, and thesis, even though point that these are research specific or ETDs, but for our problem statement, these can be considered as stop words or noise, which don't add much value to the topics we're trying to uncover. Now, there's no adaptive process to handle all this academic data, and this is where an experiment of utilizing LLMs, specifically GPT-4, was an idea that was used. The algorithm or the steps to do this are simple. Um, you first extract the top 2,500 frequent words from the ETD corpus and divide it into five groups of 500 words each and write a prompt for GPT-4. I'll show the prompt in the next stage. Um, Now, for each set of 500 words, we generate academic specific prompt that will be shown, and we query GPT-4 to basically get us the stop words that it thinks it should be noise according to the domain. And we perform a validation step because we still need a human in the loop process because um, we have observed some words are still picked by a large language model, which might not be a stop word. So that's where we combine the original lists provided by these popular libraries with an LLM assisted list, and finally validation by a human in the loop would be a useful approach because it has saved hours of analysis, manual analysis that a human would um, do into just a couple of minutes. Um, yes. So, what I mean by human validation is that words like learning and image were considered stop words according to GPT-4, which might be true in some cases, but not all cases, because learning and image are important concepts in computer science. Let's say machine learning still has the word learning, and image recognition is something that is a widely used concept, and image is a still important um, word. So those were preserved from the list provided by GPT-4, and we had 320 domain-specific stop words added to a list of 1,086 words that were finally consider a baseline to for the stop word list. Now, I will show you the results, but the impact was significant where after this custom pre-processing pipeline, we improve topic coherence by filtering this irrelevant noise. Um, yes. Now, the final step is to actually give input to the topic model, and we have an enhanced text representation, which is also part of our custom pre-processing pipeline. So, what do we mean by enhanced text representation? We have removed the stop words, but now the next step is to give useful information to the model to process it. Now, we combine the title, the abstract, and extracted keywords into an enhanced text field, an extra column that will be used as input. Now, what do we mean by extracted keywords is we have used Keyword, which is an important library or a useful library these days that extracts keywords from a given text. So you're just um, extracting an example would be an abstract regarding a computer science paper and words like if it were software engineering, uh, s- software engineering, web development, and similar terms from the abstract, provided they are in the abstract, would be extracted by this model, and we just enhance this text field with the most important words that it should consider, which is also an additional step that we wanted to use. See if topic model actually gives us coherent topic words in this case. So we compared it with uh, just the titles, abstracts, titles plus abstracts, and just the keywords. And the first, the most useful model here was per topic, which is also the best performing, which will be shown in the coming slides again. And enhanced text field had much better performance compared to just using abstracts as input for these topic modeling algorithms. Now that we have our data ready for the topic models, we needed to develop and enhance these topic modeling algorithms. And what are the different topic modeling approaches we have considered? We have used this data set on LDA, which is a baseline probabilistic model that's always used in at least 90% of topic modeling research work as a benchmark model to compare. And the more recent neural models, such as the neural LDA and prod LDA, are some of these algorithms that might help us get better topic coherence. But also, our main focus was on models that leverage these large language models. Um, and BERT topic, especially here, is basically a method which clusters these language embeddings or vectors or word representations while maintaining context and semantic richness, which is why it's more popular, where it's clustering different themes, which is essentially what we're trying to do. And that is how we extract topics or words from it. The various evaluation metrics we have used here are the CV semantic score, the CV coherence. Coherence, as I mentioned, was interword, meaning how coherent the words within a topic representations are, and topic diversity, meaning how different are the actual topics and how much overlap is there within these topic representations. Now, again, I talk about embedding coherence because language embeddings. Uh, these representations of words that maintain context and semantic richness can be used to actually compare these topic representations to also identify if the words are actually coherent and related. And the purpose of utilizing all these different types of metrics was also to have a comprehensive model evaluation and also balance the traditional methods versus the newer embedding based metrics and see if they actually align with each other. As I mentioned in my previous slides, per topic was the best performer. The next step is to narrow down to a single more best performing algorithm because the next step is to actually enhance the best performing models outputs using large language models in the end. Now, BERT topic I mentioned as the best performer was because the coherence and diversity and everything was high, and um, the embedding models or the language model that we used were from Hugging Face, um, which is open source model repository where you can use various libraries to download models or use them. Now, this also offers something called a massive text embedding leaderboard, meaning there's a leaderboard for the best performing language embeddings or the LLMs that can be used for various tasks. And for the embedding models, we used BERT, base, and case because BERT topics base model was the BERT model, which it was built on, and we wanted to see if um, the base benchmark version of BERT topic uh, is performing as well as using a CDE small one, which is an Alibaba um, model. And now the reason why we think BERT topic works better is because of the reason that I stated a few minutes back, because the contextual embeddings or these embeddings which essentially hold context, semantic richness, and everything together and have a meaning for a particular word. Now, if you're clustering all that, that is a good approach to find hidden themes or topics, and that is the reason we think the intuition between the model architecture and how the algorithm works is the reason it's the best perform. Now, what is the remaining problem? Um, the remaining problem is still that the topic model just gives you keywords as outputs or topic representations. Now, keywords might make sense sometimes, but not always. Now, what does that cause? That causes users to struggle and understand these topic representations. These outputs might not be best useful in downstream tasks such as browsing or searching. And that is where we integrate large language models as a post-processing step or everything after uh, we did to enhance interpretability of these topic representations. How do we actually design the prompt for these LLMs? The first step was to identify what different topic representations are possible with the prompt. And the system prompt just sets context that it's an expert in topic modeling and natural language processing, and that it needs to maintain consistency and clarity while providing meaningful insights. Now, um, we came up with three um, topic representations, which are key phrases, which are built on top of these keywords, and labels, which summarize the topics into 3 to 5 descriptive words, or descriptions, which are 2 to 3 sentence overview of these topic modeling or the topic models representations. Now we did this for each of the topics separately, But then the issue was that it took a lot of time. An example would be for the following topic representation. Now, I think this will give you better idea of what I'm talking about. Now, let's say there's a topic, and this is the actual output from our model and data set. We have words like health, child, participant, social, etc., which you get a clear idea about. But the prompt helped form short labels, key phrases, and descriptions. And the language model we used for this was GPT-4. And for this given topic, the short label that was formed was health and social well-being. Key phrases um, are child health, social well-being, depression studies, health intervention, etc. But also it does a good job, at least on the first um, pilot run that I did. I felt that yes, this is useful because it gives me a better idea of what the topic is, and I would much prefer these topic representations over keywords once I looked at them. Now, yes, we did create a prompt for each of these representations, but we needed something that was more consolidated, or a prompt that would create the three different representations at the same time in a single step. This is because once this seemed like an experiment or research that will be useful, comparing the different language models was the natural next step, and we used GPT-4, Llama 3 variants, and Mixtral as part of the comparison study that we did for amongst these LLMs. We mainly used OpenAI API for the GPT outputs, but also used Grok Playground, which was to test open source models like the Llama 3.1 and Mixture. And it is a chat interface where it gets all the different language models in the same um, into the same environment, and you can navigate through different language models at the same time. Now, these were the five language models we used. As I mentioned, the three variants of the Llama model, GPT-4 and Mixture. If you see, we've used Llama 3.2 3 billion, which is essentially the number of parameters or no, uh, knowledge, uh, if we can think about it as knowledge. But we wanted to compare different sizes of models while also comparing open source versus paid alternatives amongst this. So the selection was based on this criteria, and we felt this was a good mix of language models to use. However, we would need to evaluate these topic representations as well. And um, we talked about embedding based similarity or embedding based coherence. Um, when we mean embedding based coherence, we mean that we are comparing the similarities between words or two different entities. It can be within the same topic, or it can be from different topics, or it can be a topic versus a category. Now, if you remember from the earlier slides when I mentioned the data sets, we are using something called the curated data set, which is worked on by another researcher um, to map each row to a ProQuest category. And we had a good division of samples for each of these categories. Now, we compare the similarity of these descriptions against these categories, but not only categories, but also the original topic keywords to see how close um, the descriptions or the key phrases or the labels are to the original topic representations, which are the keywords, but also see if they actually align with the already existing category system labels, such as the ProQuest category. Now, the second step to evaluating these representations was also to conduct a user study to understand clarity, relevance, and accuracy of these representations. And the representations are later also ranked uh, based on user preferences, meaning we ask whether we ask the preference of each user and rank each representation. Um, Now that we have the experiments, I would next jump into the results and discussion. Um, the section is mainly outlined towards the three research questions that I showed you in the earlier slides, which was to understand the impact of our custom preprocessing. The custom preprocessing meaning where we used LLMs for stop words, but also used it to enhance text. Now, also to compare different topic modeling approaches. We already know the answer, but I wanted to show what different metrics um, pointed towards. And finally, I mentioned the LLM enhanced results that I'll discuss with you. The custom pipeline enhanced uh, the performance of all models in general, but more particularly, if you see, uh, bird topic was the most useful model here, performing the best, followed by LDA, which is um, still a useful algorithm, as I mentioned. And I know these are a lot of numbers, and I just don't want anyone to get confused. Uh, the main patterns were that pre-processing benefits were more significant at lower topic counts. What I mean by topic counts is we get to select the number of topics that we need when we define the topic model. And the ideal number for the data set we used was key equal to 15. And we um, we suggest that tailored pre-processing investments need to be done if we are to u- um, build applications for browsing and searching. And the CV score uh, significantly improved, but the topic diversity was still not something that was uh, changed drastically. And the largest gains, as we know, were by per topic. And but topic, the performance of topic modeling approaches itself, but topic um, consistently outperformed, meaning it has a score of more than zero point 0.6, which is the ideal number, and 0.74 was something that was really impressive with the approach we took. However, yeah, there's an important observation here, the topic diversity itself. LDA still is the best for getting diverse topics. Now, ideal use cases for this are bird topic can be used for searching precise interpretable topics and can be useful in academic search tools, while LDAs can be used for exploratory analysis to understand more themes that are present. Um, I already mentioned and gave an example of the three-level structure to our um, topic representations. Um, and these are still a few examples that I wanted to show before we talk about the GPT-4 um, results itself.
Hey, Prad, just a 10-minute
Yeah,
heads
yeah,
up here. We have 10 minutes remaining. Go
yeah.
ahead, please.
I'm going to. So thank you for that.
Sure. Sure.
Um, yes. Okay. I'll summarize each slide because I seem to think that there's a lot of information on each slide, but I'll just walk you through the summary of each slide quickly. Now, there's something called perfect agreement, and perfect agreement is something when I said we compared the ProQuest categories, and that occurs when all three topic representations are similar to the same ProQuest category, and we observed 11 of the topics had all the representations um, point to the same ProQuest category, which was really an uh, useful observation for us. And highest matches are for geology, material science, and political identity related concepts. Um, I also talked about scalability analysis. We did it against 333,000 documents because we found out that there were at least 100,000 documents that could not be used either with missing abstracts, titles, and other such data. And the scalability went uh, in a mixed way where we feel more custom pre-processing is required for bigger data sets. So dividing it into smaller chunks and approaching it the same way that we did is a useful alternative to um, do this rather than applying it to all the documents at once. Yes. For the user study, we used 15 topics because that was the ideal number, and we had four different representation types. We used seven participants from various departments, but the target was, however, 40 participants, including faculty, graduate students, and researchers. Um, we asked the user to select best 10 topics that they want to answer from and then rate their accuracy, clarity, and relevance, and then rank each of these representations based on overall effectiveness and clarity. Um, there was an ideal distribution, even though a few topics were less answered by all these participants amongst the 15 topics that we wanted to evaluate. Um, we understood that the best overall performance was for uh, labels. However, key phrases were uh, I'm sorry, misspoke. Key phrases are the best overall performing topic representations, dominating in accuracy, clarity, and relevance. While overall, the key phrases, labels, and descriptions were much more preferred over the original topic keywords. And for clearness and effectiveness, we have identified that different representations excel in different contexts. But overall, as I again mentioned, LLM generated outputs were preferred over original topic keywords. Yes, there are limitations to the user study, but sample size was small, and we want to cover more topics and generalize the outputs and expand the participant pool uh, to validate our findings. Yes. To quickly conclude, yes, preprocessing has actually improved coherence and diversity with diminishing returns at not ideal topic counts. And BERT topic was the best model, while LDA still maintained better topic diversity, but LLMs overall are directional in our findings that they are more favored representations over original topic keywords. We will improve on our user studies, but also implement temporal analysis and real-time integration into a search system, while also giving the opportunity to users to interact with the topics involved. I think I went over my time, but thanks a lot for listening. I know towards the end I had to rush, but any questions that you have?
Well, Prad, thank you so much for being able to break down such a complex topic into something I think that most of us could fairly easily digest. It was way above my pay grade to understand
Uh,
the magic that you all, as computer scientists, do, but we're very grateful for having you there. So maybe I'll just start off with my own question and let people maybe prepare in the chat, or you can raise your hand. But I think related to the end user who uses these applications, and I'm thinking about the reference librarian, for example, who helps the graduate student do their literature review to begin the research in their thesis or dissertation research area. So my question is, to what extent does appropriate prompt engineering enter into the search and discovery process when using AI applications such as this?
Yes, that answer keeps changing over months, I feel, because yes, prompt engineering is really important, and I follow a four point strategy to maintain proper context and make sure that it has guardrails. Now, yes, there are different prompt engineering techniques that you can use, and people are coming up with newer ways to do it. But yes, following a proper strategy by providing exactly the context and the outputs that you require are at least at a base level required for any prompt. And uh, yes, at a base level required for any prompt. And yes, prompt engineering is something that is more adaptable, and there's no one single formula for it. You need to trial and error it always, as everybody knows. So, yes, but coming up with a prompt that is going to help you is always an ongoing process, is what I feel. I hope I answered your question.
Oh, yes, yes.
Uh,
I'm still just amazed by the magic that happens using these applications. But it is, again, very dependent on the end user and their ability or skills to manage those sort of prompts in the system. So we had a question from Liz. She says, "I may have missed. How did you choose the ETDs to be in the curated data sets?"
yes. Uh, Yeah, I briefly mentioned it, but it's an ETD data set that was created by a PhD student in our lab, and that was for a different task of classification and other um, other related research work for ETDs. And the ground truth for ProQuest categories was needed. Uh, I mean, the ground truth was needed, and the ETDs that were chosen were to have equal sample size while comparing the ProQuest categories and ensure coverage is there for um, more possible um, categories and topics within a diverse range. So I hope I answered the question, but
Uh,
yeah.
and then we had Ed Fox. Ed, I'll invite you to unmute if you'd like to answer this or ask this in person, or if not, I'll read it from the chat. Ed, I don't know if his screen froze or. Uh, oh,
So,
here we go.
Yeah.
so Prad, can you kind of explain how this system you built could be used in different ways? Those are the two questions in the chat.
Okay. Um, yes, Dr. Fox, thanks a lot for that question. Um, For search and discovery, it goes much more than just doing topic modeling. But topic modeling can be an important addition to any of these systems that we build. And knowledge graphs are a concept that or a work that is done by many researchers these days, and including one of our co-authors, Satvik. And um, he is using these topic keywords into as nodes in a knowledge graph, and that knowledge graph is aiding to build a search and discovery system that can browse, search, or recommend ETDs. Now, yes, standalone, it can be a useful tool that can be used, provided um, the clustering that happened with the topic modeling is also tested and tried well. So, yes, I think. Uh, then-
Were there any other questions? We have 1 minute before we're concluding this session here. Or Prad, did you have any parting remarks? Or Dr. Fox, for that matter?
I just am reading Dr. Fox's questions and seeing if I
Ah,
covered everything.
sure.
Um,
You're very thorough.
So I think the point is that this system could be used by an ETD author or by a university librarian or
Yes,
others to improve what we
yes,
have as representing an ETD. And
yes,
they also could be used to look at your corpus and see what topics are being discussed and to
yes,
summarize that for the university.
yes, yes. Yes to all that. I think you um, summarized everything. Um, the whole presentation. Um, so yes, Dr. Fox, I agree with what you said. It is a useful tool for librarians, provided there's a good user-facing interface that can be accessible to everyone and usable, which I think other work in this conference is also covering. I to close, I just wanted to say that I spent good 2 years of my degree doing this valuable work and seeing similar work being done and how all of it can come together is something that just really made me happy and would like to really thank you for the opportunity to present here today. So, yes,
Well,
that's
thank you
just
so
it.
much, Prad and colleagues, for sharing with us.
Yeah,
So, without further ado, I'd like to invite everyone to navigate back to the main Zoom room. We're going to just have a brief toast and celebrate the evening. And please, everybody, help me to thank Prad for the wonderful presentation. And so, we'll see you on the other side in a moment. Thank you so much.
thank